Hello friends, today we are going to discuss concepts called backtracking. Okay, backtracking technique. Now remember that there are problems, right? And we are going to solve the problem by applying some different algorithm technique. As you have studied many algorithm technique as of now, but some problems are called computationally hard problem, right? And some problems will not have exact method to solve the problem. We are going with the approximate method, or one by one you are going to try some methodology to solve the problems. So similarly here we have a concept called backtracking, where we are going to find all possible solutions, all feasible solutions, right? Even though you got some solutions, we are not happy with that. We are going and finding all possible solutions, or you can say that all feasible solutions you are going to find out. And what is the technique is called here? That technique is called backtracking. As in past we have discussed DFS concept, depth first search concept. In similar way, by applying depth first search for each and every iterations to perform backtracking. Under this we have a topic, right? There are three topics we are going to discuss. One is backtracking, second is branch and bond, and third is NP complete and NP hard problems, right? First we are going to discuss backtracking. Under this backtracking we have different algorithms, right, that we are going to discuss one by one. So let us see that. In this backtracking we have a backtracking general method, solutions using backtracking to NQ problems, sum of subset problems, graph coloring, and Hamiltonian cycle problems under backtracking, right? There is another problems algorithm technique is called branch and bond. What branch and bond does? Branch and bond technique is going to find out the optimal solutions. Okay, I'll repeat. Backtracking, we are going to find out all feasible solutions, right? It means we'll have more than one solutions for the given problems. Minimum one solution, more than one solutions for the given problems. But in branch and bond, it is going to find out optimal solutions among all the feasible solutions. It means most of the time we'll be having solutions called unique solutions. That will be the optimal. If you are talking with respect to distance, minimum distance, with respect to profit, maximum profit. Under this we have assignment problems, traveling salesperson's problems, and knapsack problems. And those knapsack problem and traveling salesperson's problems we have already discussed in the past by using different algorithm technique called dynamic programming. Thereafter, last topic of this module is NP complete, NP hard problems. Under this we are going to discuss basic concepts, non-deterministic algorithms, right, polynomial, and these NP hard classes we are going to discuss at last. Let us see that first what is backtracking and how we are going to use this backtracking concept to solve the problems. Remember, backtracking eliminates some unnecessary cases from the considerations and solutions in reasonable time for many instances, but worst case is still exponential. Remember that it used to take more time to solve the problem. Suppose you have to make series of decisions, right? Because you're going to find out all feasible solutions, and say at one time you have two different or three different options to choose, right? So we are not going with only one case, we are going with the case one, choice one. I will see that whether you are getting feasible solutions or not. Again, choice 2 we are going to apply whether you are getting feasible solutions or not. Choice 3 you are going to apply whether you are getting feasible solutions or not. So we have many decisions to make among various choices where you don't have enough information to know what to choose, right? Each decision leads to new set of choices. Some sequences of choices, possibly more than one, may be solution to your problem. Backtracking is a method or methodical way to trying out various sequence of decision until you find one that works. It's not necessary that whatever the choices you are made, right, that is going to lead to the feasible solutions or it will give you the solutions. No, sometimes you are going to apply the method and you are not able to find out, by satisfying all the constraints, all the conditions, any solutions, and it leads to dead end. Dead end means what? Thereafter we don't have any further choices to make it out, right? So such cases, what will happen? Again, you are going to backtrack and we are going to find out, is there any other possibilities to find solutions for given problem. Using backtracking, we are going to find all feasible solutions, as I said. Now, let us see that backtracking algorithms. Backtracking is really quite simple. We explore each node as follows. Backtracking can be thought of as searching a tree for a particular goal. Remember that when you are talking about the goal, it means what? In a decision trees, it is called leaf node. Like we are going to draw a state space tree. I will come to that, right? So our goal, our solutions will come at the leaf node level. So leaf node point either will have the dead end when you are not getting the solutions, or will have a proper goal, means the solutions that you are going to call it as a feasible solutions. So goal is here leaf node. We explore node n. If n is a goal node, then return success. If n is a leaf node, return failure. Remember that n is a goal node, right? We are writing success. Otherwise, you are saying that failure, or we can say dead end, right? For each child C of n, explore C such that if C was a successful, return success. Otherwise, return failure. So this part you are going to check, and you are going to see that if child node of given parents node is leads to the solutions, yes, it is a success. Otherwise, if it is fail, then we are going towards the parents node positions, means previous level, and try to find out any other child node or which node is going to leads to a particular solutions. Let us see that what is main part of this algorithm is to construct a state space tree, right? And this state space tree will give you, right, whether solutions are there or not there. We are going to represent in the form of a state space tree, right? Here we'll have nodes, those are the partial solutions. We have edge, choices in extending partial solutions, as we'll have in the graph node and their edges. But remember that in this, we are going to explore the state space tree using depth first search. As I said you in the introductions, we have already studied depth first search. We'll go in depth way until unless we'll encounter with dead end, or we are encounter with a success point, goal point, right? In that case, again you are going to backtrack. So basically you are going to apply DFS. If you are encounter with the dead end or success, again we will go back and finding any other possibilities. Now here we have non-promising nodes, right? There are two types of nodes we are going to call: non-promising nodes and promising nodes. What is non-promising node and promising node? Let us see that. Solutions and, right, we call a node as a non-promising if it cannot lead to a feasible solutions or optimal solutions. We call a node as a non-promising if it cannot lead to feasible solutions or optimal solutions. Otherwise, it is called promising. It means we have a set of nodes which leads to the proper solutions, feasible solutions. Those nodes are called promising nodes. DFS stops exploring subtree rooted at a node that cannot lead to a solutions and backtrack to such nodes parent to continue the search. As I repeat it again. Let us see that very important problems under this backtracking is called n-queen problems, and we are going to solve this n-queen problem by using backtracking concept. What is n-queen problems? I believe all of you have already played the chess. So here we are talking about n-queen problem means what? There are n queens, and we are going to place those n queens on n by n cross n chessboard, right? And we all knows that property of queen, right? It can move in vertical directions, it can go in horizontal directions, and even it can traverse in diagonal. Okay, so that is what movement of queens on the chessboard. So that is why it's mentioned here, place n queen on n by n chessboard so that no two of them are in the same row, same column, same diagonal. Remember that if more than one queen you are going to place it in the same row, same column or diagonal, what will happen? One queen will be captured to other queen. So we have to place the queen, n queen on n cross n chessboard such a way that one queen is not going to capture other queen. That is the problems. Now in queen problem, the object is to place queens on a chessboard in such a way that, right, no queen can capture another one in a single move. And in standard we are going to discuss 4-queen problem. When you are talking about the 4-queen problem, then 4-queen problem, 4 queen can be placed in 4x4 chessboard, right? Again, rule is remain same. If you are going to place one queen at the first place, we are not going to place any queen further in the same rows, right, and same column or same diagonal, right? So we can see that if I am going to place it over here, we are not going to place these all part. Not here because it will get cancelled. Not here, it is diagonal. We can place it over here, right? So there are other possibilities, right? In order to find out the feasibility. This is one of the solutions where you are going to place 4 queen successfully without cancelling others. And that is what we are going to make a state space tree for this particular problem. So let us see one by one how you are going to solve this problem. So this is the ideal format of 4x4 chessboard, and we have to place 4 queens, right, as is visible here, right. Let us see that. Friend, if it is n is equal to 1, right, then there are 1 queen and you have to place 1 cross 1 chessboard. It means what? We have only 1 block, and we can place 1 queen because 1 queen we can place, there is no other queens to capture. So we are getting here in this particular case when n is equal to 1, we are getting 1 solutions. Right. Now say n is equal to 2, then you have to place 2 queens, right, where in 2x2 chessboard, 2x2 chessboard, right. In that case, how many places will have? 2x2 means there are 2 rows, 2 columns. Now look, we have to place 2 queens. Based on the rules, queen can move in horizontal directions, vertical directions and diagonal, and 1 queen will capture other queens if we are going to keep in the same row, same column or same diagonal. So let us see that. If you are going to place first queen over here, can you place it here? No, right? Can you place it here? No, it is same column. Can you place it here? No, it is a diagonal, same diagonal. So 2x2 chessboard, how many queens you are able to place? Only 1. So in this case, are you able to place 2 queens? No, only we have placed 1 queen, hence no solutions. So remember that 2x2 chessboard we are getting no solutions, where 1x1 chessboard we are getting 1 solutions. Let us see that in third case, when n is equal to 3. If n is equal to 3, what will be the chessboard? Chessboard will be 3 cross 3, and we are going to place 3 queen on the chessboard, right? In that case, we are going to make 3x3, 3 rows, 3 column, right? Let us start from here. We can place 1 queen here. Yes. Can we place here? No. Can we place here? No. Can we place here? No. Here is the same row, here is a same column. Can we place here? No, it is in same diagonal. Can we place it? Yes, we can place it here, right? So 2 queens we have placed. Can we place it here? No, it is the same column. Can we place it here? No, it is the same diagonal for the second queen. Can we place it here? No, it is the same column for the second queen. How many queens we have placed? 2 queen. How many are supposed to place? 3 queen. Hence, no solutions. No solutions. Right? Even if you start from the second positions or third positions, we will not get the solutions for 3 by 3 chessboard. Okay. That we can explore. We can start from the second place or you can start from the third place. I will discuss in the normal state space tree for the 4 queen problems. These all are the basic things we are going to discuss. Now let us discuss state space tree for 4 queen. We can see that this is our normal 4 by 4 chessboard. Okay. Now we have to place 4 by 4 queens on 4 by 4 chessboard. 4 by 4 chessboard. That we have already drawn. Now, can we place it here? Yes, we can. So we are going to make from, if you are going to place it in the first row, first column, then we are going to take the line from here. Second column, we can start from here. Third column, you can start from here. Fourth column, you can start from there. So let us see that we are going to start from here. Now, we are going to make solutions for this. First queen, if I am going to place it here, what will happen? Next, can we place next queen? We are not going to place any queens in this complete column. We can think of first row information is over, right? We are going to place it in the second rows, right? So in that case, can we place it in the second row here? No, we cannot place. Can we place it over here? No, we cannot place. Can we place it here? Look, here is the same column, here is the same diagonal, here is no problem with respect to the diagonal. So we can place it in this particular place. So we are going to make again decision. We see that that decision will lead to wrong decisions or true case that we have to say. Okay. One queen place it here, second queen we have placed it here, right? Now next, can we place this place? Can we place another queen next level? Because we are going in depth way. First we make the decision of first queen at the first place, then accordingly we are going to make the another set of queens placement, right? So after placing 2 queens, now third queen you can place it in the third row, because first row 1 queen is done, second row 1 queen is done, third row we are going to place it the third queen. We see that we are able to do it or not. Let us see that. Can we place it here? No, it is the same column. Can we place it here? No, it is the same diagonal for the second queen, right? So this is also gone. Can we place it over here? No, it is the same column. Can we place it here? No, it is in the same diagonal. So you cannot. Let us see if one of the rows of n queen problems, if you are not able to place any queen, it means only we have left with the last row, and last row we can place it 1 queen, right? Not here, we can place it over here. So out of these, how many queens you are able to place? Only 3 queens, right? In that case, out of 4 you are able to place 3 queens, hence we are not going to get any solutions from here. We are not going to get any solutions from here, right? So hence we will start doing backtracking, right? Why we are start doing backtracking from here? Because third row we are not able to place any queens, hence we are having shortage of space, even though you are going to place 4th queen in the 4th row, right? But out of 4 queens, we are able to place only 3 queens, hence we are not going to get any solutions. So this kind of scenario, we can stop and say it is dead end, and we are going to say that no solutions, right? Because you are able to place only 3 queen. So what will happen? We'll go and backtrack. Is it possible to do these positions in different places? Yes, we can have second queen, you can go in the 4th position. So if we'll go from here and we try to explore what will happen, whether you able to make any solutions or not. So let us see that. First queen is here. Here we are not going to place. Already we are doing third. We are going to place it as the 4th positions. 4th, 1, 2, 3 is done. 1, 2, 3 is done. We are placing second queen as the 4th positions. No. Next iteration. Can we place the queens here? No. Because in the same vertical. Can we place it here? Yes, we can place it. So third queen we can place it over here, right? So this is possible. Can you place it here? No. Here? No. So what will happen? Once you are going to place this queen, just I will give you the pictorial views to understand. Alright? This scenario is like one queen, second queen, and we are able to place the third queen here. So you can say that in this place we have third queen. Right? After this, 4th queen, can we place it over here? No. Same column, same diagonal. Can we place it here? No. Same column. Can we place it here? No. It is a diagonal to these elements. Can we place it here? No. Same column, same diagonal to the first element. So in this particular case, we are not able to place 4th queen. Right? So out of 4, how many queens are able to place? 3 queens. Right? Out of 4, how many queens are able to place? 3 queens. So this part we are not getting, here we are not getting, here we are not getting, here we are not getting. So 4th row we are not able to place any queens. Hence, there is no solutions. So in this case also, we have discussed in the next page and check that we are not getting any solutions. So no solutions from this side. Then what is left? We have checked with the first positions with all position of the second row and we are not getting the solution. It means from this child node we have to go to the parent node and see that what is the other position is possible. So we have started with first positions. Why not we can go with second positions? Yes or no? We can go with the second position and we will see that what is happening. So let us see that we have started with second positions. We started here, Q. Now, for next iterations, can we place it the queen in this place? No, because same diagonal. Here, no, because same column. Here, no, it is the same diagonal for the previous queen. Can we place it here? Yes. This is the place we can place it. So we are going to make the decision and we are going to check whether other queen we are able to place it or not. If it is, then we can see that. So first queen, second queen. No, next queen. Can we place it here? This is done. Again, third row we are going to start from the beginning. Can we place it here? Yes, it is not diagonal of this. It is not in column. It is not on row of the previous queen. Hence, we can place it here. So this will accept 100%. So let us see and discuss in the next page that these possibilities when we have queen here and here is already filled, right? We can go for third row this place. If we are connecting it, we can see that placement of the queen 1, 2, 3. So third queen is done, right? Now next iterations, we are not going and checking with the third row because third row one queen is placed. There is no scope of placing other queen because one queen is going to capture. Hence fourth row. Can we place it over here? No. Can we place it over here? No, because it is diagonal to this element, this queen column, this queen diagonal. So you cannot place. Can we place it over here? Let us see that. This is not diagonal for this. This is not diagonal for this. there is no queen in this column as well, hence we can place it here. So this is going to be one of the solutions. So let us see that. I will show you that a solutions I projected in previous slides that will match with this. So one queen, second queen, third queen and fourth queen. Based on this a complete scenario is satisfying all the conditions of 4 queen on the chessboard 4x4. So 4 queen is already placed successfully, hence this is one of the solutions. This is the solutions for n queen problems. We see that this is the second position, fourth position, first position and third positions. We can see that position in first row is second, position in first row in second, position in second row fourth, position in third row first, position in fourth row 3. So these all are the position of the queen we are getting, and it is one of the solutions. This is one solutions of 4 queen problem. Now question is there any other possibilities? We can get any other solutions or not? Yes, that we can try. As I said you that in n queen problems you are not going to stop there, right? Once you are getting the solutions, not getting the solutions, in both the cases we are going to traverse back as you are doing in DFS concept. You backtrack it and try to find out any other possibilities. Is there any other feasible solutions based on the promising node, right? So just I am trying to show you these solutions, what exactly I shown you here. So this is one of the solutions. We can see that position of the queen, first row second positions, second row fourth positions, first positions, and so this is the position of queen 2 4 1 3, right? So we got the solutions for n queen problems. Now let us see that is there any other possibilities are there or not in space tree. Yes, let us see that. Second place we have seen. Can we go, because this is a blank. First place we already traversed, we are not getting solutions. Second positions we got the solutions, right? So this is state space tree we have taken to the next page. Can we place it from the third and see that whether any possibilities is there or not? Let us see that. So based on this decision, first queen we are going to place it not first, second we are going to place it at the third place, right? If that, then we are not able to place any queen further in this row, we will go to the next row. Can we place it queen here? Yes, it is not in the diagonal, it is not in the same row, it is not in the same column, hence we can place it. So we can go with this, and let us see that. First queen, second queen. Alright. Now, second row is done. In third row, can we place it the queen here in the very first positions? No, because it is in the same column and it comes in the same diagonal of the first queen. Can we place it here? Yes. This place is not comes in the same rows, same column, right? Can we place it here? No, it is comes in the same diagonal. So this is failed. Here, it is comes under the same column of the first queen. Failed. Can we place it here? We can see that it is not comes under the same diagonal, same rows, same column. So here you can place. Here you can place. So let us see in the next page on how you are going to discuss. So what we got it here now, it is like this was the state, and we have said that it is not possible here, it is not possible here. So is it possible here? No. So here we can place. Fourth positions you can place. So let us see that. First queen, second queen, third queen is done. All 3 queen you have placed. Now, again, we have to place the new queen means what? Last row. Can we place it over here? No, because it is in the same column. Can we place it over here? Yes, it is not in the same row, same column, same diagonal to any of the queen. So hence this is the right place. We can place it the new queen. I am going to conclude something very interesting for n queen problems. So first queen, this is the second queen, this is the third queen, this is the fourth queen is placed. So how many queens we have placed, friend? 4 queen, and it is 4 by 4 chessboard. So hence this is one of the solutions. This is one of the solutions. Now if you see that position of the queen in the chessboard, first row, third column, so third positions. Second queen, second row, first positions, and third queen, third row, fourth positions, and fourth queen, fourth row, second positions. 3, 1, 4, 2. So if you see that compared with the previous solutions, it is just a mirror image. If you keep the mirror, we can read 2, 4, 1, 3 is one solution, 3, 1, 4, 2 is another solution. 3, 1, 4, 2. You read from the right hand side, 3, 1, 4, 2 is another solutions. So we got 2 different solutions, right, for n queen, where n is equal to 4, right. Remember, when you have discussed n is equal to 1, we got 1 solutions. N is equal to 2, we got no solutions. There is no solutions possible. N is equal to 3, we got no solutions. N is equal to 4, we got how many solutions? 2 different solutions. 2 solutions you got it, right? And both the solutions we have already discussed. Remember that similarly, if you try for n is equal to 8, right, we will be getting 92 different solutions. How many solutions will get? 92 solutions will get. It means there are 92 different ways to place the 8 queens on 8 by 8 chessboard. But in exams, they will ask you up to 4 by 4 chessboard. About summary, backtracking technique is used to find all possible solutions. But what is happening, it is little faster than brute force technique. How it is that, let us try to focus on this. When you are applying the brute force technique, we are going to apply from here first. So first queen we have how many possibilities? 4, 4, 4 and 4. Out of 16, any 16 out of 16 place, you can place it at one place in brute force. For second queen, we will be having 15 different positions to select. But in backtracking, what is happening based on the queen property, each and every queen got each and every row, how many number of space we have. So first queen, we got maximum of 4 space. Second queen got maximum of 4 space. Third queen got maximum of 4 space. Fourth queen got maximum of 4th space. So if you see that total number of space is required to perform the task in backtracking is 4 into 4 into 4 into 4, right? It is 256 different place, different ways we can place the queen. That is a combination of promising node, non-promising node. While in brute force, as I said you that first queen there are out of 16 place, 1 place. For second queen, out of 16 place, 15 place we have. For third queen, out of 16 place, how many place we have? 14 place. Likewise, we are going to apply 16 into 15 into 14, so and so. So there are many different iterations. It will take a lot of time to solve. But again, I am telling you, backtracking used to take more time to solve the problem, right? Backtracking only use when other direct algorithm is not working at. Thank you very much.